So 6.2b will be all about the applications of right triangle trig. In 6.2a, we refreshed our memories on SOHCAHTOA, on how we can use these trig ratios to solve for a missing side or missing angle. So today we'll just be doing the same thing, but in the context of a story. Recall that to solve a triangle just means to find all 6 components, 3 angles and 3 side lengths, that make up the triangle. And the reason why we study trig, the reason why we study right triangles is because there are a lot of things in life that can be described using right triangles. You'll see right triangles in construction, surveying, navigation, astronomy, so on and so on. The list is near endless. Basically, any situation that you want to indirectly measure something that might be impractical otherwise, that is the job for trig. So how do you think people figure out how tall mountains are or how far away planets are? It's all trig. So because it's just an application of 6.1a, there isn't any new concepts per se, there isn't any new techniques or new ideas to teach, but I do want to introduce some vocab words. When you're doing these problems, they may say something like angle of elevation or angle of depression. As this image right here sort of suggests or explains, the term angle of elevation just simply means the amount of angles up an object is from your field of vision. So if you imagine yourself just looking straight ahead, straight forward, don't tilt your head up, just look straight forward. The amount of angles you would have to tilt your head up to look at an object is what we call the angle of elevation, and conversely, the amount of angles you would have to tilt your head down is what we call the angle of depression. So just be mindful of those terminology. There is another terminology, angle of inclination. If the amount of angles you have to tilt up or down is on a physical ground, like the side of a mountain, the side of a hill, then we call it angle of inclination. You'll see example differentiating the two here. Now, anytime I do word problems that involves real life stuff, geometrical shapes, circles, squares, triangles, whatnot, I always draw it out. So that's my hint to you. Draw it out. Let's take a look at this first example here. So suppose a giant redwood tree casts a shadow 532 feet long. I want to find the height of the tree if the angle of elevation of the sun is 25.7 degrees. Now, I'm not an artist, so typically my drawings consist of dots and lines. So let's go ahead and draw this out. We know we have a tree somewhere, so here's my giant redwood tree. There's my tree. It's not perfectly straight, but oh well, who cares? It's a sketch. I know this tree will cast a shadow, so here's my shadow. I know the shadow is going to be horizontal because shadows exist on the ground. And they do tell me that the shadow is 532 feet long, so I can go ahead and do that. And it tells me that the angle of inclination of the sun is 25.7 degrees. So from the tip of the shadow, the angle to go up to the sun, so I'm going to draw an angle up to the sun, I know this is 25.7 degrees, and I want to know the height of the tree. So there's my variable. That's it. So this should be just 6.1a again. Here's your picture, solve for the missing side. So again, my hint is to look at the information you're given, look at the thing you want to solve for, and ask yourself which trig ratio connects them all. Well, relative to the angle, this h is an opposite, this side length is an adjacent, opposite, adjacent. That makes me think of tangent. So just write down what is true. In this problem, it is true that the tangent of 25.7 degrees is equal to the opposite over the adjacent. And then this gives you an equation to solve for h. Multiply both sides by 532. And since 25.7 is not a special unit circle angle, you'll just go ahead and just whip out your calculator and type that all in. So if I were to punch in this guy here into a calculator, that will give me the height is approximately 256.03 feet tall. Easy peasy. Right? So this is an example of using trig to measure something that's impractical. It's easy to measure things on the ground. It's easy to measure shadows, but it's not as easy to measure vertical heights. But with trig, we can. Let's take a look at a more involved example, right? The second example here. So this second example says, from a point on the ground 500 feet from the base of the building. So I know I have a building somewhere. So here is my building. There's my building. And I'm at a point 500 feet away. So I'm going to be 500 feet away. So there I am, 500 feet away. An observer finds that the angle of elevation to the top of the building is 24 degrees. Well, that's easy. So angle of elevation to the top of the building is 24 degrees. And the angle of elevation to the top of the flagpole. Oh, so there's a flagpole up here. So here's the top of the building. But on top of the building, there's a little flagpole. So here's a flagpole, right? And from the same point, the angle of elevation to the top of the flagpole atop of the building is 27 degrees. So from the same point to the top of the flagpole, I'm telling you this entire guy is 27 degrees. Find the heights of the building and the length of the flagpole. So I hope everyone agrees that this is a two-part question. It's asking us two things. It wants us to find the height of the building, which I'll call H here. And I want to find the heights of the flagpole, which, I don't know, F for flagpole? Who knows? So how do we do this? Now remember, we can only work with right triangles. So you want to suss out, or you want to find as many right triangles as possible. Hopefully it's very easy to see one right triangle, this guy here. And we are lucky that it utilizes the one side that we're looking for. It utilizes H. So I can just work with this small right triangle and see which trig function I can write. So again, just focus on the information you're given. So in the small right triangle, I have the angle 24, I have the side length 500, and I have the side length h. I ask myself what trig function relates all of them together. So relative to this angle, h is opposite, 500 is adjacent. Opposite, adjacent, we are using trig, we're using tangent again. So there we go. I know, just by looking at the picture, that tangent of 24 degrees is opposite over adjacent, and then I can multiply both sides by 500 to solve for h. So pop that guy into my calculator, you get 222, about 222 and 0.6 feet tall. Now I want to solve for the flagpole, but unfortunately, if this is the length of the flagpole, he is not a part of a right triangle. That little sliver is not a part of a right triangle. So you have to do the next best thing. Is the flagpole's length a part of a side that is a right triangle? And I hope everyone can see that the flagpole height is, actually let me use a different color, is a part of this right triangle. So you can see that the yellow side length, F, is a part of the bigger right triangle. So since we're working with the entire side length, you have to remember that this guy here is F plus H. So this is, again, highlighting, this is the triangle that we're working with, and then this is the information that we're working with. Right? So we're not using the angle 24 anymore because the big triangle uses the angle 27. So I asked myself again, which trig function relates all the information together? I hope it's not too complicated. Everyone can see we have opposite and adjacent again, so it will be another tangent, right? Because relative to this angle here, this side length is opposite, this side length is adjacent, so we'll use tangent. So let's write down the true statement. Tangent of the angle 27 degrees equals the opposite side. Now again, the opposite side is F plus H. So this will equal opposite F plus H over the adjacent 500. And then you just go ahead and solve for F. So I'm going to multiply both sides by 500. And then to solve for f, you subtract the h. So f equals 500 tan of 27 degrees minus h. We know what h is. Oh, that covered it up. We know what h is because we solved it in the first part. And this guy here, you just pop it into your calculator. So if you pop everything into your calculator, you get the flagpole to be about 32.1 feet tall. It's a really big flagpole. So there you go, an example of using trig to find heights. Last example here. Like I said, there's no new teaching involved in this lesson, just a whole bunch of examples just to get your some ideas in mind. Reading it, it says a woman is standing on a hill. A woman that is standing on a hill sees a flagpole that she knows is 60 foot tall. So I can go ahead and write that in. So I know for a fact that this entire length here is 60 feet tall. She knows that. The angle of depression from to the bottom of the pole is 14 degrees. It's already marked in our picture. And the angle of elevation to the top of the pole is 18 degrees. It's already marked in our picture. Find her distance x from the pole. So we need to find this length here. Now remember, we're dealing with right triangle trig, so I can really only work with right triangles. And I hope everyone can see in this picture, we actually have two right triangles. We have this top right triangle, and we have this bottom right triangle. So I can only utilize those pictures. Well, okay, so let's do this. What is the only numerical side length information we're given, though? We're given this length here, the length of the flagpole. So I have to somehow incorporate the sides of the right triangle that relates to that length. Well, the only thing that relates to the flagpole, I hope everyone can see, is this side here, the yellow, and this side here, the blue. Because they didn't label anything, I have to use my own labels. Let's call, I don't know, this, I can't use X because I already use X. Let's call this A. Now, I could call this B, but remember what I said before. The more variables that we have, the more complicated the problem tends to be. Well, since I already know the total, right, the total is 60. Let me use a different color because that's sort of confusing. So let's make this guy 60. Since I know the total is 60, if this part here is A, then this right here has to be the leftover. It's 60 minus A, right? Because that's what's left over after you take away A from 60. So now I can go ahead and sort of build my equations, right? So let's work with the yellow triangle. What information do I have and what am I looking for? I have this angle 18, I have this side length marked, I have this side length that I'm solving for. Relative to the angle 18, A is opposite, X is adjacent. What do you know? By sheer coincidence, we have tangent again. I apologize, guys. It seems like everything is tangent, but it doesn't always have to be. Sometimes you might use sines or cosines. But for the yellow triangle, I can just see that tangent of 18 degrees is A over X. Now, what is it that I'm solving for is I'm solving for X. But remember, I have two variables here, so I actually can't directly solve for X. Instead, what I'm going to do is I'm going to solve for A just because I don't like fractions. So I hope everyone can see here that A equals X times tangent of 18. Now, why do I bother? Well, if we look at the blue triangle and we set up an equation, so relative to this angle, we're looking at the blue triangle, we have this side length, we have this side length. Not surprisingly, we have opposite over adjacent, we have tangent again. Relative to the blue triangle, we have tangent of 14 degrees equals opposite over adjacent. Notice that we can now plug this A here into that A. So this is actually a systems of equations problem. So then let's go ahead and do that. Tan 14 equals 60 minus A, not A, 60 minus x tan 18 degrees over x. Now I can go ahead and solve my problem, right? So multiply both sides by x. I want to get all the x's together. So notice how this guy has an x here. So I'm going to move him to the left by adding. So I'm going to add him over. And Algebra 101, if you have multiple pieces, this piece and this piece, that both contain what you're solving for, we're solving for x, the technique is to factor out the x. And then now this makes it easy. The last step is just to divide it all out. X equals 60 over tan 14 plus tan 18. Now, as ugly as it looks, this guy here doesn't have any variables, and x is by itself. This is our answer. So all we have to do, because 18 and 14 are not special angles, we just go ahead and take a calculator, pop them in, and we get about 104.48 feet. So that's how far away the woman is from the flagpole. So, like I said, no new learning in terms of background logic, background concepts. 6.2b is just 6.2a, SOHCAHTOA, Trig, but with word problems. So the only way you can get better at word problems is to practice. So give it a shot. Good luck.